the concept of IoT is that how to connect the things to the internet, right? And now understand connection of things to internet, right? So this is basically things to internet is basically, you can say, Internet of Things, right? So the purpose of this IoT is connecting the things to the internet. So what is the thing here? Thing can be anything. Either it may be digital entity or it can be physical entity, whatever. So now you so now you will understand how the physical entities can be connected to the internet and what does it mean basically. So so what is the objective of this IoT? So IoT is trying to create a new world, right, in which it is trying to connect the everything around the globe to the internet. Either it is human, either it is animal, either it is plant, either it is home, either it is your refrigerator, everything will be connected to the internet, right? Answer. So why we are connecting things to the internet? That we can access our things around the globe from everywhere, right? So it is not that easy to access that thing. It includes a lot of things inside it, right? It's not that easy that thing is going to connect to the internet and you can access it, but it's not that easy, right? So today we will understand how this process is going to take place and how basically our cloud computing plays a good role, right? Because now you see we are connecting things to the internet, and even cloud services are basically we can access to the internet. So right now you can understand the correlation between them, right? So they are basically having typical a single point of convergence, right? Yeah, so they are having this single point of the convergence over the internet, right? So that's how the cloud is basically responsible to provide the services to the things, right? What services? Because when you're connecting to anything, it must be communicating via some data, right? This must be generating some data, and this data need to be processed to get some meaningful information, right? So that's how and how to be communicated, how it will be computed data over the internet because of the cloud or maybe some computing infrastructure. So you can understand the relationship between cloud and Internet of Things, right? So see, Internet of Things is basically what? Internet of Things is nothing. It is just a, you can say, business entity to the cloud, or you can say it's a kind of a Internet of Things is the technology that is creating the business to the cloud. Please understand this concept. The Internet of Things is the entity or maybe technology that is creating the business to the cloud. What is the job of cloud? To perform computation, storing the data, everything. Then when you will basically publicize your cloud, because your customers will be more. So see, everything is going to be connected to the internet, and automatically your customers are going to be increased. So now let us begin up with this IoT. So see, this IoT is not a new concept, right? It was started from 1992 onwards, right? In 90 or maybe on before that. So you can see that how many devices, approximately 1 billion devices were connected in 1992. So as long as this, cloud computing infrastructure was developed and high bandwidth, yes, 1 million devices were connected in 1992, and 0.5 billion were in 2003, and so on, right? So now you can see almost 50 billion devices are connected in 2020, right? Over the internet. How it was evolved? Because in early 1992 we were lacking in terms of internet communication technologies as well as the wave, right? So nowadays you can see that wave 2.0, wave 2.30, wave 3.0 are helping a lot to make this technology comfortable to be executed over the net, right? So see, this is the evolution of the connecting devices over the internet. Till now we are dealing 50 plus, right? It is the statistics about 2020. So we are having 50 plus billion devices over the internet, right? Different industries are giving different definitions. So it is International Data Corporation, right? So it gave a definition, IoT is a network connecting devices or things that is characterized by autonomous provisioning, management, and monitoring, right? So ultimately, the IoT is innately analytical and integrated, right? So here you can see that we can connect the things to the internet. Even we can do some provision and management and monitoring via software, right? Ultimately, when we talk about automation, it is just via software. So it is a definition given by the IDC. Similarly, if you see this Cisco perspective, then Cisco says that IoT is the next evolution of the internet, right? It's the next evolution of the internet, connecting the unconnected people, even process, data, things in your business today. So IoT is basically next evolution of the internet as per the Cisco, right? If you see, definitions are emphasizing over the computing, right? Because the purpose of IoT is to connect the things to the internet. But what do you mean by connecting the things? We are connecting via some sensors, right? We are connecting via some digital devices, right? So these devices or sensors are able to produce some data. Or obviously the connection has some meaning. Why we need to connect? Because we want to get some information. Why we people are connecting? Because I want to learn from you or you want to learn from me. So ultimately there is a computation, there is a processing that we have to do. The same way when we talk about the IoT, the sensors and the actuators are connected to the internet, right? Not all the internet, but to some computing devices. It may be cloud, it may be fog, or it may be some your on-premise system as well. Because when we connect something, it generates some data, and this data is not meaningful unless you do not do some process over that, right? So when we perform some computation, then we get some meaningful information. Then we can take certain actions with respect to the entity that was connected to the internet, right? So see, this can be connected. This is allowed to connect several real world people, animal, agriculture, plants, everything, right? So these are the many definitions given by the many industries. So this is one standard definition that is given by the IEEE Internet of Things Journal. It is world's rank 1 journal in the field of IoT. The recent, you can say, research or you can say top research is being published in this journal, right? So this journal gave a basically typical definition. An IoT system is a network of networks where typically a massive number of objects, things, sensors, or devices are connected through the communication and information infrastructure, right? To provide value-added services via intelligent data processing and management for different applications. So applications can comprise smart cities, smart health, smart grid, smart home, smart transportation, smart shopping, even smart education, or nowadays, if you realize a smart industry, right? So that is basically, we talk about industry 4.0, so that we will understand how it has been derived from the IoT, right? So see, this is, typical definition. So ultimately what the purpose, we are connecting the set of things to the internet and doing certain process and getting some meaningful information, and on the behalf of that information, we can take certain intelligent decisions regarding control, process, or management purposes, right, for the different applications. So this is what IoT. Okay. So if you see here, there are the some other you can say other definitions are also there, but yeah, nowadays there are few terms that you need to know. One is IoT, that is Internet of Things. One is IoE, Internet of Everything. One is WOT, that is whatever of thing. It is mostly, it is more irritating word, right? Because nowadays everything is going to connect to the internet. Either it is animal, you can see from this picture, either mobile phone, ambulance, industry, animal, right? And human, vehicle, home. That's why the people are giving the different terminologies, right? It is Internet of Everything, whatever of thing. So they are giving different terminology, right? So don't worry about this. Everything is now Internet of Things, right? So, let us go to the bit technical. So now question is coming, how things are able to connect to the internet? How we can connect the things to the internet? Very simple question. So see, there are the two important concepts. There is one is the physical thing, and second is the virtual thing. So physical thing, basically it exists in the physical world and are capable of being sensed, actuated, and connected. So you can take the example, industrial robots, human goods, or you can say electric equipment, or maybe your telephone, your mobile, your laptop, computer, animal, everything can be as the physical entity. So the question is that if this physical entity could be connected by itself, then it could be done more than 100 years back before, right? So it is not possible to connect the physical thing directly. There is another concept that is called virtual thing, right? So virtual thing basically exists in the information world and are capable of being stored, processed, and accessed. It can be multimedia contents, application softwares, or many more things, right? Or maybe text data, it may be numeric data, anything, right? Or maybe analog signal, digital signal, whatever. So see, from this picture, you can understand what the idea. See, we have this block is denoting the device. It is denoting the physical thing, right? So you can see Yeah, I2E is International Telecommunication Union, if I'm right, right? International Telecommunication Union, if I'm right. Please do on Google. Yeah. Okay. So see, what is interesting thing is here, every physical thing is connected with some device. If you see here from this picture, what is this device? This device can be some microcontroller, maybe some microprocessor. It may be some sensor with microprocessor. So when we connect these two things, then they are able to connect over the internet, right? So that's how that physical thing cannot be connected to the internet until unless you are not connecting it first with some device, and this device is able to connect to the internet, right? So ultimately, what we're trying to do, we are changing the physical things into the virtual thing. So now once it is able to convert, when it is able to transform from physical thing to virtual things, now ball is in our code, right? Our code means an IT domain. So now we are able to connect to the things. So ultimately, you can understand from this picture, first things are being connected to some device. It may be microcontroller, microprocessor, which is able to generate some digital signal. Then this device is able to connect to the internet. So this is what basically Internet of Things, right? So in the same way, you can connect any animal, you can connect any, what I say, people or human, anything, right? So I hope now you get an idea that how to connect, things to the internet, right? Without any microcontroller, microprocessor, you cannot connect anything to the internet, right? So another question is why IoT? Because IoT uses the open platforms, right? So it is it is easier in terms of deploying the applications, and faster and secure and more accessible from everywhere, because it works over the open platforms, right? And it allows to create you low power wide area sensor networks, even personalized area networks, even machine to machine communication networks, or ubiquitous sensor networks that you can access around the globe. So you can see there is a flexibility in terms of creating personalized networks which are suited for a typical service or typical application. That's why people are most of the time creating their own networks using the different technology that we can discuss about it later on, right? And it contributes to social economic development, and people are using a lot of you can say a lot of IoT devices in order to develop the prototypes in agriculture, health sector, transportation, and the interfaces among the different devices are basically very friendly, right? Or you can say very user friendly, so they can be easily connected, right? So that's why people are going for this IoT. If you see the typical characteristic of this IoT, that you can see that it is low cost, and you can say it is low power, long battery duration, right? And high number of connections and different bit rate, you can say requirement, long range network you can establish, and low processing capacity devices you can utilize if there is not requirement of high-end computing facilities, right? And low storage capacity device you can also use, and small size devices you can also utilize. If you see what I see, if I do I have picture or not? Yeah. See, this is the one device that is called Raspberry Pi, right? This device is sufficient. It is operating over the 5 voltage approx, and this device is sufficient to do the all job that you can do over laptop or machine. So you can understand, and the cost of this device is almost 5,000. Almost 5,000. This is called Raspberry Pi, right? So you can understand this device can do almost each and everything. So such devices can be used for developing the prototypes, and these are really helpful in different designing different prototypes in different domains. So that's why people are keen to go towards this, right? If you see that some perspective of this Internet of Things, want that anytime, any place, or anything can be connected to the internet, right? What do you mean on anytime? On the move, or outdoors, indoors, night and daytime, you can work with the you can work with it, right? And you can connect things human to human, human to things, things to human, or maybe you can represent human by animals and anything, whatever, right? Or it can be able to work in any place. It can be air, water, land, space, wherever. So now people are basically thinking about of even utilize the IoT devices over the space as well, right? I will show you the one of the example later on. So if you see here, if you typically go for the IoT reference model, so let us see what is this IoT reference model, how this Internet of Things is becoming a successful technology. So what are the different layers here? So see, first it is the age. right? And this edge is basically holding some sensors, devices, and machine. Those are basically able to transform your physical things to the virtual things, right? It means they are able to generate some data that can be on the top of the data we can work on, right? So this first layer is basically typically responsible to generate some data, right? And second layer is basically connectivity layer. So obviously these things, what do you mean by things? Some sensor devices which are already connected to some other things. For example, animals, plant, or maybe home appliances, many more, right? So ultimately, we want to connect them with some computing paradigm, right? So this second layer is basically connectivity. So it may include the 4G, 5G, wireless, NB-IoT, right? Or maybe LoRa, Sigfox, Zigbee. There are many Wi-Fi, wireless, Wi-Fi communication. There are many communication technologies. As per your application demand, you can use different technologies, maybe Bluetooth as well, so on. So second layer is responsible for the connectivity. Now, obviously, first layer is generating some data. So on the top of data, we want to do some computation, then only we will have some meaningful information, right? Then this information will be helping us to make certain decisions, right? That we can use to achieve something, right? So here, this third layer is basically called edge computing, right? So here, what we try to do, this edge computing concept is driven from here. So here we have the two choices. Suppose if the data is very small, or you can say light data, then we can perform the edge computing, right? Either this edge computing can also be replaced by the fog computing. So please hold on these two terms. I will discuss them in depth, right? So today's session is all about this computing, right? So see, this layer is basically responsible for the edge computing. Right now, you understand, this layer is responsible to provide some light computing. It is not typically high-end computing facility will be there, right? It's just light computing. So based on this computation, you can generate some meaningful information, right? Or meaningful data. You can extract out of this whatever has been sensed at the bottom layer, right? So then fourth layer is called data accumulation. So this layer is responsible to store this data. Maybe you can use in real time, or maybe you can use this data in future as well, right? So on the top of this data, you can perform certain data aggregation and certain data analysis, or some computations to infer some more meaningful informations. So these two layers are responsible for high-end computing. High-end computing, right? So these two layers are high-end computing. So this is responsible by having high-end computing facilities. Either it can be in your premise or maybe on cloud, right? So cloud, you cannot leave whenever it is required high-end computing facilities, right? And on the top of, we have a one layer that's called collaboration process. So you can say it is basically application layer. So what was the purpose for this IoT that will be satisfied, or that will be executed typically on this top layer, right? Why do you form this IoT network? This will be basically satisfied at the top layer. Either you want to utilize this information for some business purposes, either you want to utilize this information for some maybe industry operations, or maybe some making control decisions. Either you want to get some monitoring information. So everything will be happened at this top layer, right? So these are the civil layer, you can say reference model for the IoT. What you can observe here, if you divide this layer, then you can see, you can divide this, phenomena into the two concepts, right? Or you can say two terms, that is called IT and OT. So IT is information technology and OT is operational technology. So the data, or you can say all these steps, all the layers comes under the operational technology. And these all layers on the top of comes under IT. That is what information technology. Right? So information technology, what you can do, you can perform certain computation, you can put some security constraint, you can do some management, you can take some management decisions, so on, right? What do you mean by operational technology? So operation technology is responsible to flow the data basically. Then how data is going to flow from one stage to the other stage, right? So this is basically called operation technology layers, right? So the data here in this layer is data will be in motion, and here data will be at rest. So here you can perform certain operations to infer some meaningful knowledge, or meaningful, statistics, or maybe other analysis, right? So this is what you can say typical sequence of the steps in the IoT, right? So now we see what is the relation of this IoT with the industry 4.0. So now we can understand, see, this is the picture that is going to show you the typical evolution of the industry 1.0, industry 2.0, right? And industry 3.0 and 4.0. As you remember, I'm not going for the 1.0 and 2.0, 3.0, so on. So you remember very well them. Here, here you can see that you can say steam-based engine, train engine was developed. Here, electricity was developed. Here, you can say electronics-based, CMOS-based circuits were developed. So it was basically you can say Industry 3.0 was responsible for designing the mainframe computers, supercomputers, or high-end computing servers, right? Now, what about the Industry 4.0? So Industry 4.0 is typically based on the cyber physical system. Basically, you can take a look over the slide. So cyber physical system is basically connecting your physical entity to the cyber entity, right? So what is physical entity again? So physical entity means human, people, animal, or maybe things, everything can be there. So these things are going to be connected to the cyber world. What is the cyber world? Cyber world is basically again IT world. So this cyber physical system is the, you can say, new terminology, right? But it is typically defined by the 3 C's, right? So one is computation, communication, and control, right? So you can see this communication, computation, and control need to be automatized in the cyber physical system. Or you can define the cyber physical system. It is an engineered system whose operations are monitored, coordinated, and controlled and integrated by a computing and communication code, right? So ultimately, everything need to be automatized in the cyber physical system, how entities are communicating together. So this is what we call, another term is called Industry 4.0, right? So basically, if you talk about the Industry 4.0, what that is simple way. So Industry 4.0 is basically it is the combination of IoT and AI. So obviously, if you see that it is built on the top of Internet of Things and is generating the data because of the billions of the devices are connecting to the net, right? So IoT is generating a lot of data. And where this data will go, who will manage it? That is the responsibility of this cloud, right? So wherever you're talking about the data, big data, you cannot skip the cloud because these all technologies are working over the ubiquitous computing. Ubiquitous computing means around the globe, you can access from any point, right? So whenever the concept comes of ubiquitous computing, then you have no choice. There is a concept of cloud computing, right? So here you can see this is and so that's why you cannot skip ubiquitous internet and computing. So this is what cloud, right? So now you understand what is going to be happen in the Industry 4.0. See, so Industry 4.0 come after the IoT. The role of IoT is to basically connect things to the internet. Now, what is the Industry 4.0? Industry 4.0 wants that things should communicate automatically, and they should be able to take certain decisions based on the communication or based on the machine-to-machine communication. So what is that? Let us take the example to understand this Industry 4.0. Let us, with the help of IoT, now you have connected your refrigerator, suppose, to the internet, or maybe your mobile app or wherever internet is, right? Suppose you have a refrigerator in your house, so it is going to be connected to the internet. And now, so refrigerator is now a smart refrigerator, right? So now what we want from the Industry 4.0, suppose you have a milk and you are in the habit of taking coffee every morning, right? So suppose the milk is not in a freeze. So your freeze should be able to understand whether milk is not there and my boss is sleeping, and morning my boss will take a coffee. So now it is the responsibility of refrigerator itself to arrange the milk for you in the morning. So what would be happen? Your refrigerator, suppose this is your refrigerator, it is connected to some network that is called internet, right? And suppose it is having sensor, it will check there is no milk in the refrigerator, automatically it generates one signal, it will send to the internet. So internet is what? It is maybe some cloud. So over this cloud, there might be some application that is running to manage your home appliances, right? There may be some application. So signal will be some signal will be sent over this internet to the cloud, and here some machine learning or AI-based algorithm will be running in this particular application. That is ML or maybe AI-based algorithm will be running over this cloud, and this ML and AI-based algorithm will be able to predict the signal, why the signal is coming. So obviously this algorithm will analyze it is coming because no milk in the freeze. right? So based on this I mean ML or AI based algorithm might be having some application that is having directory of all the nearby shopkeepers around your location where you are going to sleep, right? So obviously this location might be taken by the smartwatch that you are going to wear while you are at your home. So that based on that, this will send the signal to the one shopkeeper, right? So maybe there will be a nearby shopkeeper, right? So this will send a signal to the shopkeeper that you need to transfer a milk or 1 liter milk to this particular location. So this shopkeeper will send some person and will send one shopkeeper will send his guy to deliver your milk to this particular location, right? So this is what it is going to be happen automatically. So this is the phenomena of industry 4.0. So same thing is going to be applied in the industry automation, right? So this is going to be the future, right? So now you can understand the role of cloud. So everything will be managed when you talk about the ubiquitous computing by the cloud only, right? So similarly, the same thing can be managed when this person is going to shift from Delhi to Bangalore, or maybe Bangalore to Ahmedabad, so, or maybe around the globe. So same thing will be managed because this application is running over the cloud and it is going to be accessed around the globe, right? So this is what industry 4.0. So industry 4.0 is basically IoT is responsible to connect the things to the internet, and AI and machine learning is basically responsible to make certain decisions, right, based on its computations, because AI and machine learning require high-end computing infrastructure. That's why these services are expected to be running over the cloud only, right? So, and another thing is to perform the computation to AI and ML algorithm, we need high-end computing facility. So that is what our cloud computing, right? So that's why. So these technologies are basically leading to what I say. This new emerging era that is called Industry 4.0, right? So obviously now you understand IoT obviously includes cloud itself, right? Then IoT plus AI becomes the Industry 4.0 in very simplest way, right? So that's why we need to understand what are the typical stages in IoT. So see this 4-layer very abstracted model of IoT. So here in IoT, we have one topmost thing that is very necessarily, that's called sensing and identification. And on the top of, we have the connectivity and then computing and then integrated applications, right? Then you must be having some regions. So let us take, these things, what are there? So see, first sensor, right? So sensors need to connect it to the internet, okay? Without sensors, as you remember, without sensor, you cannot connect the things to the internet. Okay. Suppose you want to connect with someone, right? Maybe someone means, or maybe something. Suppose you want to connect to hot water. How would you connect? You will use your sensor, right? First, you will put your hand to that water, and then you will get some data from that that will be reflecting to the brain, right? That it is hot, right? Because what data is being sensed by your sensor, that will be processed by your brain, that is CPU. Then it will generate some signal. Yeah, it is hot. So then you immediately remove your hand, right? So then you will take certain action. So same thing is going to be happen in the IoT, right? You can relate this with the human activities and how human perform. Obviously, Stansi is saying first we will use eyes to find water. Yeah, exactly. So it is not only that you are using one sensor for one particular job. You can use multiple sensors, right? Even you can use your actuators as well. You will go by walk to that particular place where is the water, right? So see, these actuators and sensors work in collaboration, and you can use multiple sensors and multiple multiple actuators to perform a certain job. For example, nowadays you remember one autonomous vehicle, right? Or you remember the Tesla car, or you must be might be hearing about it, right? So Tesla car does not use only one sensor, right? When it go on the road, it has a set of sensors, maybe some IR sensor, or maybe some it may be some temperature sensor, or maybe some you can say obviously the Sudhanshu is saying a lot of them, exactly. So there are a lot of sensors. So based on that, you first get some data, and then you perform some computation over the data, then you make certain decisions, right? So let us typically, I hope you understand the typical meaning of the sensors. So if you take the real life example of the sensor where we practice it more, in real life. So see, sensor was used when you design the aircraft with the autopilot system, right? So in the autopilot system, you have this first sensor. So sensor is going to measure the position, height, speed, temperature, and location of a particular flight, right? So basically, sensors are acting in this particular system as the input entities, right? So whatever is going to be basically sensed by the sensors, it will becoming like a input to the computer, right? So computer is what? It is the computing infrastructure. If you go nowadays for the IoT application, this computer becomes your cloud, right? Now computer has been replaced by the cloud, right? So here in the typical flight system, sensors generate some data and they forward it some computing entity. It may be computer, it may be cloud, it may be fog, edge, whatever, right? Then this computer process something, and based on that, it generates some output. So it might be having some algo or maybe some program that is able to take certain decisions based on this data, right? So this, sorry, it is not able to take the decisions, it is able to generate some decisions, right? So this is the algorithm, this will generate certain decisions. So what is decision in the typical autopilot aircraft system? You may turn off or turn on the engine, you can flaps, or you can turn on the motor, you can perform rotations to the wings, so on, right? So these are the decisions taken by the your controller. So basically, this is the typical example that where you realize the sensors in real life applications, right? So let us take the typical definition. Converts the signals from one energy domain to the electrical domain energy. If you talk about the sensor meaning in terms of IoT, right? So it is going to basically sense the changes in the it is going to sense the change in the different energy domain, right? And it is going to convert it into the electrical domain, right? So these domains can be physical, chemical, and electrical properties, right? So it is going to basically change, it is going to basically measure the changes in the chemical, physical, and electrical property of some, right? And then it is going to convert them into the electrical domain. So it might be useful when you connect to the sensor to the basically computing system, right? So ultimately our computing system basically works over the digital things. So ultimately this energy from the electrical domain can be converted to the digital data. So this data can be processed by any of your algorithm, by any of the computing system, right? So sensors are basically nothing, they are just going to change, they are going to notice the change in the physical, chemical, or electrical property, right? And they are basically providing the respective output signal in terms of electrical signal, right? This is what basically sensor, right? So if you talk about the sensors, they can be classified in different contexts. So one can classify the passive sensors and active sensors, right? So passive sensors basically consider they do not basically they use an external power to be functioning, right? And active sensor does not utilize the external power, they have itself energy to basically perform these certain operations, right? And similarly, you can classify the sensor in two other ways, either analog or digital way, right? So analog sensor basically produce the analog output, and digital sensors generally produce the digital output, right? So here you can see the typical, examples of the sensors. These you can utilize in your, maybe you are experiencing in your cars, vehicles, everywhere, right? So temperature sensor, proximity sensor, accelerator sensor, IR sensor. So see, the sensor either will be in the analog category or maybe digital category. Sometimes some sensors are here, they can be in, or they are able to function both the ways, either analog or digital. For example, motion sensor are coming, they can work either in digital or analog way, right? So these are the set of sensors that you can use for the different purposes. Or maybe in different scenarios. So people are using. So ultimately, the job of the sensor is to generate the data, nothing else, right? So the respective data will be generated, and this data will be again transformed into the computer understandable language, right? Or computer understandable data, right? So this is the basically one of the entity of the Internet of Things. So first you need to place the sensor near to the things. So it will sense the data from that particular thing, and it will generate the data that is able to understand, that is able to understand by the computer, right? And another, model of this IoT is called connectivity. So thing is that how would you provide the connectivity, or how would you, what are the possible way of connecting the sensors to the internet, right? And what different kind of networks are basically possible, that we will take a look here. So see here, see if you see that there can be classification in different ways as per the understanding of different peoples. So the one can be coverage zones, right? So according to the coverage zone, you can classify the networks in the two different categories. One can be rural or remote, and one can be urban or dense urban, right? So see, whenever you are going to form a network connection, either in rural or remote, or maybe urban or dense, basically they have a different ranges, right? The same technology, if you are going to implement in the rural, then it is having higher, higher range. If you are going to establish it into the urban areas, it will be having lower range. So what is the reason for that? Anyone would like to answer? Why it is so? If you're using it as an open field, if you're using it in open field, then its range will be high. If you're using it in a basically flat or dense building, its range will be low. The types of network that can be allowed in the IoT, that is basically you can create the personal area network, local area network, or low power wide area network, or maybe machine to machine communication network, satellite based network, and you can say opportunistic use of spectrum. That's called white space. It means sometimes some spectrum band is not going to be utilized. This can be also utilized for some special services with the help of this IoT. So IoT is giving you to form a different kind of networks that I will show you next slide. But what are the possibilities there, right? If you talk about the spectrum use, so you have the, again, you can classify the networks into two classes. One can be unlicensed or one can be licensed one, right? So unlicensed networks are free, but they are not secure. Licensed networks are secure, but they are obviously expensive, right? And even you can also create the some network based on the public network or maybe private network if you're talking about some commercial services, right? So let us see what are the, possible ways of or what are the possible connectivity options in this IoT. So you can see you can find the unlicensed spectrum LPLA, it means low power local area network, or maybe you can having low power wide area network. So you can see you can use a licensed LPWA, maybe satellite space network, or maybe PMR is basically a personal mobile radio network. It can form for the some military operations as well, right? And here you can see licensed spectrum for IoT, MTC, and here you can see that NB-IoT is basically narrowband IoT network, right? It can be in licensed form because it is always licensed. It cannot be unlicensed, right? So see, based on this, previous classification, what are the possible you can say technology nowadays you can experience in the market, right? So you can see here this type of these categories comes under the short range, and most of these categories comes under the long range. Okay. So, and this LoRa router can connect to the another LoRa router around the region where we are going to set up a network. And another person with the help of Bluetooth can connect to the LoRa router. And with this way, they can communicate without having an internet facilities, right? So see, nowadays technology has been evolved in different ways. So LoRa is nowadays very interesting network that's called long range network. I will show you its range. It can communicate 10 to 20 kilometers with a single router, right? So this is right now in its infancy state. It will be evolved very soon in different ways, right? So let us see here. These are the some similar network. They can be used for the long range, at least 2 kilometers to the 20 kilometers onwards. So here it is Sigfox, LoRa. So even you know that 4G and 5G, and here you can see some wireless networks. So these networks, maybe Wi-Fi, they can be used to communicate the long range communication, right, between the devices. And here you have some short range options that's called Zigbee, Threads, and Z-Wave. And here even you can go for the Bluetooth, depend on your range. And it is near field communication, that is the NFC, right? So there are nowadays many technologies are there. So basically we use the short range communication for the sensors or actuators in general, right? When you want to communicate to devices at the different locations, maybe in kilometers, or maybe in obviously in kilometers, then you go for the long range. So ultimately, if you understand this complex architecture, the short range devices can also connect to the long range by having some common network, either Wi-Fi or maybe wireless or Ethernet, or maybe some cellular network. They can integrate together, or either utilizing satellite network. So ultimately, they can send their data to some cloud storage, right? So the job of this, why we need to communication? Because we want to transfer some data from one source to another destination. So ultimately, in the IoT, the destination is your some place where you have a storage and computing infrastructure. So that is what your cloud. Here you can perform some computation or some analytics. Based on that, you can take some business decisions, or you can basically utilize that information for other, for other applications as well, right? So this is your complex, you can say, architecture, is complex architecture in general that you can use, right? How can you use this LoRa technology? Whether it is supporting, then it will be allowed. See, LoRa technology is what? See, there is LoRa is having its own router. Okay, let me talk about what is LoRa. LoRa is having its own router. That is this router, right? Now you can communicate with this LoRa router by using some LoRa supporting devices, right? LoRa supporting devices. It is having kind of some small tiny client devices, right? So this is also supporting some Bluetooth connections with that particular device. So this device can also be connected with the Bluetooth connections. So you can communicate with the LoRa router with the help of only LoRa device. LoRa device means LoRa client device. So here you will be having LoRa device, right? And this device is able to compatible your mobile by some with the help of Bluetooth connection as well. So then you will be communicating with this LoRa device, and this LoRa device will be responsible to transfer its signal to the LoRa router. Similarly, the same thing will be happen to the other side. This is one side. Same thing will be happen to the other side, right? So in this side, you can connect with the LoRa router with the help of LoRa device only. That's what LoRa client. So if this LoRa client allows you to connect with the Bluetooth as well, right? So there should be some LoRa device, then only you can connect with the LoRa router. Otherwise, you cannot. Okay. So let us see this. Most you can say advanced technologies or communication technologies which are being practiced by the IoT. So one is the Sigfox, one is LoRaWAN and NB-IoT. So just we will see the few interesting property. One, you can see the frequency on what they communicate. So this you can say this Sigfox works over the 868 megahertz in Europe and 915 megahertz in North America and 433 megahertz in the Asia. Similarly, you can see for the what I say this LoRa 868 megahertz and 915 megahertz and 433 megahertz. Okay, and similarly you have a this NB-IoT use the LT kind of your licensed spectrum, right? That you basically use basically on mobile phones as well. If you talk about the bandwidth. What bandwidth uses by this technology? It uses 100 hertz only, right? And this uses 250 kilohertz to 125 kilohertz, and it uses 200 kilohertz, right? Now, what the data transmission rate or maximum data transmission rate? Sigfox can do 100 bits per second. Okay, LoRa can transfer 50 kbps, right? And it can transfer NB-IoT 200 kbps. Right. The most interesting part is that the range. If you can see the range of this particular, you can say Sigfox, it is having 10 kilometer in urban and 40 kilometer in rural areas, right? And you can see that LoRaWAN, it is having 5 kilometer in urban areas and 20 kilometers in rural areas, right? So you can understand what difference basically you can observe when you implement same technology in the rural area and urban areas, right? And here you can see that 1 kilometer NB-IoT in the urban and 10 kilometers in the rural. So just I want to know that one relationship. Suppose any technology that is having its bandwidth higher, then what is the relationship with its range? If it is having higher bandwidth, what would be the range? If it is having lower bandwidth, then what would be the range? Can you understand some relationship from this table? Reverse, right? Inverse. Yeah, exactly. So see here, Sigfox is having very small bandwidth. That's why it is able to send its signal to the longer distance, right? And similarly, that LoRaWAN is having its, you can say, almost in between than the NB-IoT and Sigfox. That's why it is having its range in some in between, right? If you see that its bandwidth of NB-IoT is highest, so that's why its range is smaller, right? That you can see here. So now these are the most dominating technology in the field of IoT for the long range, right? So see, for the IoT, we have understood the two stages. One, sensors, sensing stage, and one, connectivity. What are the connectivity options are available? Just we have gone through. Now we go for the computing. Now the role of our computing paradigms comes into the picture, right? Now you will understand the evolution, the different computing paradigms on the top of cloud, right? Why a cloud is not meaningful for this particular technology, right? Then what is the under solution? Okay, so let us see. Now now we can relate this particular session with the cloud. Okay, so see, this is a nice picture. This is showing the something that you can keep this picture in mind, so you can understand the different technologies in better way, or different basically computing technologies. So what to observe from this picture? See, understand for scenario. We have some IoT devices. Obviously, these IoT devices mean sensor, actuators, or maybe any physical things, whatever. So these devices need to communicate, right? And these devices, these IoT devices can be with respect to the smart health, different application, right? In smart home, smart city, smart farming, smart factory, many more. So, right? So these devices can be with respect to certain applications. So another question is that this, or you know very well, whenever we are connecting any IoT devices to the internet, this device will definitely generate the data. Otherwise, there is no use of the connection, right? There is no need to connect this IoT device to the internet. So this device is going to generate the data. Then how would I process the data and what are the possible options, right? So this picture is showing when you connect the certain things to the internet and they generate some data, then how this data will be processed, utilizing different frameworks. So here we can see what are the all possible ways where you can perform the computation over this data. So the first important thing you can understand, this one is the cloud. Suppose the data is going to be sent. The one possible way is that you directly send to the cloud server or cloud data center. Okay, so it can be processed here. Now, what happened for some real-time applications? This option was really not good because the data sometimes network failure can be at the source, sometimes network issue can be at the destination, sometimes can be in between. Suppose your data center in US. So how this data is going to be from this whatever transfer said. So we have the multiple stages of the connection, right? So if you're going to directly send some data to the IoT, this data cloud data center, you never know at what point you can have the failure of the network connectivity, right? So in this way, you are not able to respond in the real time. Obviously, if the connection is correct or connection is fine, then you can respond in real time. Maybe there will be some latency, right? But you cannot guarantee always that if you're processing something through the cloud, it will be always responding, right? So that was the major issue. So previously we utilized the cloud for some computation for the IoT devices as well, but we were not going for the real-time computation, right? So what example of real-time computation, suppose you are going to basically prepare one traffic light controller and some data you are going to send over the cloud. Suppose if there is a delay of 5 seconds even, then you can understand what the traffic jam will be there at the intersection, right? So for such you can say real life applications, this cloud option is not suitable. What was the other way? So people thought of the option 2. This option 2 is called edge computing. So what that is computing? We shifted some computing power to the network layer, or you can say near to the edge, right? Here is edge what? Where we are basically sensing this for data. So when we are going to basically shift some computation, so this edge is not responsible. See, if you are going to do some, you are going to design some traffic light controller. So you cannot create the data center in every intersection, right? Or in every city. You cannot do this. Or you cannot go for the creating one data center every spot. So what we can do, we can use some small computing devices. That's called edge computing devices, which can be microprocessor, microcontroller, or maybe sometime some NVIDIA Jetson or some maybe small, you can say, computing devices, which are able to process the data in the real time and respond at the spot. That is called edge computing, right? So this is the second option. This is suitable when you do not have the you can say enough when you do not require the enough computation, right? When you can say small computing is sufficient, then you can choose this option. This is a good one, right? And this edge computing is not compelled to be backended by the cloud. It is optional in the edge computing, right? It is defining its computation power independently. Suppose you have some mix-up kind of scenario. Some data you want to process in real time, and some data has some flexibility deadlines, right? So, and even you have more computational power. You need basically more computational power in the real and for a particular application that need to be responded. That is example of the traffic light controller. Because in traffic light controller, you have to sense the number of vehicles they are used. If you're using the cameras to detect the vehicles or count the vehicles, then obviously it requires a high-end computing power. So for that, edge computing will not work. What the new option? That's called fog computing. It means you can create one local data center here. It will be the data center near to the intersection, but it will not be as powerful as the, what I say, cloud data center. It will be a kind of a fog node. It will be a small server that is sufficient to satisfy the requirement of that application at this spot. Right? So this is called, fog computing. And third and fourth are the options of the fog computing. Why we are giving the third or fourth? If you need in future, then these two options can be combined together. Right? So it is called federated fog computing. It means this is what it is called one domain. This is, another domain. And each domain is holding certain servers. These are called fog nodes. Maybe servers, or maybe laptop, maybe desktop, or maybe sometimes each computing devices. It depends on the kind of services you require, right? So this fog basically, this is called one domain. One domain is holding multiple fog nodes. Fog node can be Raspberry Pi, or maybe laptop, maybe server, maybe one data center. It depends on the scenario. I cannot give a uniform. It is basically flexible. I cannot give you a strict term that fog node means this is server or only whatever, right? So fog node can also have laptop, can desktop, or maybe NVIDIA Jetson, because nowadays I will show you in the picture. Then we have the small edge computing devices. These are more powerful than your servers. I will show you some of the pictures later on, right? So see, here we have the domain 1, domain 2, and they can also interconnect together. This is called, federated fog domain. Suppose this domain is running application 1, app 1, and it is running app 2. In between, some data is being processed here and some here. But sometimes you need that app 1 and app 2 need to somehow do some synchronization activity, or they want to do some communicate together. So then they can form a network by together. That's called federated cloud. It means multiple fog domain can connect together. Okay. So this see, some data is real time, some is non-real time. So what you can do, real time data you can process over the fog, and non-real time data you can offload to the cloud. That's the concept. So, so from this picture you have a sense. Now we will understand in depth what is the fog computing and what is the edge computing, right? So you know very well the cloud computing. So obviously I'm going to skip this definition of the cloud. You know very well. We cannot define the cloud in a better way. Obviously we have the NIST definition. So you know what is the cloud. So what is the issue with the cloud, right? So the issue with the cloud is what? That is the bandwidth, right? Even we have seen, right? So there can be multiple hopes basically. If anything going to fail on any one of the hope, then basically there will be a delay in the service, or there will be a basically issue, right? Even if you see, suppose this is one stage 1, this is the stage 2, this is stage 3, and finally it is reaching to the cloud. Suppose it is having high bandwidth. Suppose it is having high. Suppose it is having suppose it is having 100, right? See this context. It is a very challenging thing. That's why this new architecture has been evolved. Suppose this is having 50 bandwidth. Now it is again having 100. So see, whatever is the bandwidth, so whatever maximum data you can transfer using this link, right? So there is no use that some of these connection are having high bandwidth. There is no use of that. Ultimately, it will work. So that's why this cloud is not successful for the real-time applications, right? So because of this, you can say, because of this, limitation, right? Or the basically Internet of Things, they are basically increasing a lot of sensors or billions of devices around the globe, right? So these are the two regions. One is the limitations of the cloud in terms of its bandwidth, and the evolution of the Internet of Things. You can say exponentially, it won't be wrong, right? So that number of IoT devices are increasing exponentially, right? And the bandwidth of cloud computing is obviously limited, or sometimes we do not have any control of the latency, right? They are basically amplifying what I say, or they are giving the new concept that's called fog computing, right? They are basically responsible to evolve the new architecture that is called fog computing architecture, right? So these are the two things. One is Internet of Things, exponential growth in the Internet of Things, and cloud bandwidth. These are the two problems or two issues or two challenges are responsible to the evolution of the fog computing paradigm. Okay. So let us take a so fog computing is basically it's very similar to the cloud computing, but it is having distributed architecture. However, cloud computing is having centralized architecture, right? So let us read out the definition of this fog computing that is given by the NIST. The fog computing is a horizontal, physical, or vertical resource paradigm that resides in between smart end devices and traditional cloud, right? So fog computing will always be in between your edge and traditional cloud, right, or data centers. You have seen this from the picture. This paradigm supports vertically isolated and latency sensitive applications by providing ubiquitous, scalable, layered architecture and federated and distributed computing, storage, and networking and connectivity. So in brief, what I'm trying to say, it provides all the services which are basically provided by the cloud. You can say it is just a subordinate of the cloud. It is the, in brief, to understand the fog. So fog computing just a subordinate of the cloud. Whatever service you can access from the cloud, all the services can be accessed by the fog. In brief, it is just a subordinate. Okay. If you see the characteristic of the fog, it is basically you can see that contextual location appear, but in cloud you do not know actual location where it is. But in the fog, you know the contextual location. Where is my data center? Where is my fog server? Right? Here you can distribute your resources at the different geographical locations. They can be known according to the locations. And here it can also be form a large scale sensor. It can be also suitable for the large scale sensor networks. They can get the real-time services from this fog node. This can be used for the certain applications like environment monitoring, disaster management, so on. You can create the different fog servers, right, for the different applications. And basically, it allows you to distributed computing and storage infrastructure, right? And very large number of nodes can be distributed into the different geographical locations. It means you can form different fog domains if you are having many number of nodes. So there is no need to put all the nodes at the one place. You can put to the different geographical locations and you can connect them via network. So they can form a same infrastructure as done by the cloud, right? And it supports the mobility of the devices. They can switch from one domain to another domain, right? It allows the smooth interface between them, and it is very helpful for the real-time interactions, especially for the streaming information. And basically, it supports the Lambda architecture. So this is one important term, Lambda architecture. So Lambda architecture basically allows the data can be processed in both ways, either in a streaming fashion or either in the batch process, right? Either you can put your data in the form of batches, then you can submit to the server. It can be processed there, and either you can process the data whenever it is coming continuously in the form of stream, right? So Lambda architecture support the both kind of computations. So basically, fog computing support both the way. It can also process the data in the real time whenever it is coming, or either you can give the data to the fog server in the form of batch. It can also do that, right? So obviously it supports the heterogeneity as it is supported by the cloud, right? And you see that some other you can say characteristics. So one important characteristic is interoperability and federation. So it means it allows to connect the multiple devices from the different vendors. Obviously it is built for the IoT, so IoT is suffering from the interoperability. If IoT devices basically are able to support this interoperability, then fog computing domain will definitely support those devices to connect over the network, right? So I hope you understand the interoperability. Interoperability that in current, it is not always true that some devices are going to be designed from the different vendors, right? They may not have a common interface to connect, right? So this is biggest issue in the IoT, right? However, it is fog computing has been designed on this particular you can say phenomena that it will in future it will provide the interoperability. All the vendors should be consented to one particular interface on the top of multiple devices can be connected together. And obviously, it also provides the federation. It means multiple fog domains as per a requirement can be connected together in the real time, or they can be interconnected dynamically as per the requirement of the applications. right? And it supports for the real-time analytics and interplay with the cloud. It means it can generate certain results in the real time, or it can also interplay with the cloud. Means it is always backended by the cloud. If suppose some load is going to be increased to the particular fog server, so based on the priority, it will offload some of the data to the cloud. So it will so processing can be done in parallel, one at the fog server or maybe in cloud as well, right? So it can basically speed up your computation, right? So it is obviously particularly well suited for the real-time applications. As you know that this technology has been evolved because of the IoT only, right? Because the IoT becoming a barrier in that sense. So again, now question is that why fogging? So I hope you have the good picture now what the region that why fog computing is important, right? So here you can see that first important point is that exponential data in real time is there is can be generated in future or maybe in current, depends on the application, right? So the region, you know that it is the IoT, right? Generated by the IoT, right? And the second region you can also think of, if all data should go to the cloud, right, for analysis and speech and everything. So obviously due to the high latency, it will not be responsive in the real time from the cloud. We cannot say that cloud cannot process that data, but yeah, the data cannot be received in the real time. It may be the probability there, right? So it may be the possibility there. So that's why this the another region for this fog computing, right? And third, you can say that some of the performance metrics, if you see for some of the real-time applications like efficiency, scalability, latency, security, bandwidth, reliability, right, privacy, could be greatly improved if you do some processing or analysis at the or basically near to the data source or basically local network, right? So that's why this fog computing is becoming more becoming a necessity for the future to come across, right? So that's why if you see that Cisco is putting a lot of effort nowadays in basically this fog computing, right? Cisco is basically putting a lot of efforts for this, just for your information, okay? So here you see that there are a few terms in this fog computing. One, you can encounter the fog node and fog domain and fog federation. So I hope I have defined all the terms. So just take a quick review to get it refreshed. So the physical and logical network element that implements fog computing services, right? Computing mode, right? So any server or maybe any computing processor that is able to compute some of the data that is considered as the fog node, right? And fog domain means you have some particular region in which that particular set of fog nodes can be connected together by a high-speed bandwidth network, and they are able to provide some set of services same as the cloud. So this particular domain is considered the fog domain, right? If you talk about the fog federation, it means that multiple fog domains can be connected together for some particular applications, or maybe for providing certain services in combinations, right? So this can be formed dynamically or as per the requirement, right? So it means it's a kind of a good cooperation based computing between the multiple domains, right? So this can be used for offering the multiple services related to the compute services, networking, storage, or maybe any of the services. Maybe it can also offer SaaS, PaaS, or IaaS, all the services, right? Whatever you take from the cloud as well. Yeah. So here you see always we have the fog computing will always basically lead by these IoT devices, right? Because without these IoT devices, we are not expecting the real-time data generation, right? So we always assume that IoT devices are at the destination. Sorry, they are at the source. They are generating this set of real-time data. They need to be processed, and they will be communicating by the fog gateway, right? So they will be communicating with the fog gateway to the you can say. Obviously, after that, it is having a similar architecture as cloud, right? They're having a broker, right? This broker will be responsible to schedule your jobs to the respective fog nodes, whosoever is available to this particular domain, right? And obviously, this broker is also responsible to perform some offloading, right? Here you can see this link. It will this broker will be so intelligent, it will analyze your data whether you want real-time processing or not. Some data might be not for the real-time processing, then it will be transferred to the cloud. It will be processed there. So that's what called offloading, right? And or the backend, it might be having some data repository. So some process data can be stored to the locally, or this link is not here. Even in future, it can also be connected to the cloud, right? So some data, if it is going to be, or you can say storage is going to full, it might be transferred to the cloud at the backend. Or maybe they can increase more storage, or either it can be shifted to the cloud, right? So this is the, I mean, typical, you can say for computing infrastructure. So you can say that fog will always be backended by the cloud. So you can say that fog will never say you that I do not have the infrastructure to serve you, despite of it is having local limited physical infrastructure, because it is being supported by the cloud. It may delay your services, but it will not say I don't have the infrastructure. Okay, the fog, what challenges we are facing now. Okay, so sometimes suppose you have a here cloud data center. So and this is suppose kind of a scenario of a real world scenario, right? Here are some offices, here some factories, some industry, here maybe some institutions, maybe so on. Yeah, so everyone is going to basically access the cloud services, right? And they are connecting through some communicating links, right? So what is going to happen nowadays? Suppose sometime you might get the power failure or some of the link, or sometime you can say that the bandwidth has been constrained to transfer certain limit of the data, right? And sometimes you can see that some latency sensitive applications are not responsive. Okay, and sometimes you can realize that suppose some link is broken, so your this part cannot be connected to the what I say cloud server, it is not able to get the services, right? That we obviously encounter this all situations in our daily lives. But so what would be happen once fog will be coming, right? So because of the fog, local data center will be created wherever you have a possibility that there is a high probability of network link blockage. Then we can put a one data center there, right? And here we can see that here are basically more real-time requests are coming from this particular region, so that we can place one more data center. So by placing the by geography distributing the data center to the different locations, we can resolve all the situations which are coming here, right? So this is the advantage of fog computing. Okay, so it will tackle all these situations whatever we encountered here in the previous case, right? So and even you can also perform the real-time load balancing over the multiple fog domains, right? Or even inside the one server. So that can be, you can see that links are going to be utilized in better way, right? So you see, there is another, term, because this is, you might not be hearing about, right? So that's another term in the computing that's called mist computing. Okay, so mist computing is basically, you can say it is very near to the data source, or you can say it is almost at the data source. So mist computing is a light-weighted and rudimentary form of the computing power that reside directly within the network fabric at the edge of the network, right? And the fog layer closest to the smart end devices using computers and microcontrollers to feed the data into the fog computing nodes and potentially onwards towards the cloud computing services. So you can understand, this definition because of with the help of this picture, right? Now you can understand what you mean by the mist computing. So this is, your mist layer. So it is saying that as per the NIST definition, it is basically rudimentary form. It means what? Suppose if you see the temperature sensor, it is nothing. Temperature sensor cannot work without any microcontroller, right? So what you can do, you can connect this temperature sensor with the microcontroller and you can put it into the land, suppose. So it is going to, or maybe you can put it into your room or maybe somewhere else, right? Wherever you want to measure the temperature. So see this microcontroller that you are attaching, maybe Arduino, you can track with that. So see this Arduino will be taking the data from the sensor and it is processing here itself. And some meaningful information it is sending to the upper layer. This layer can be either edge computing, either fog computing, and further fog computing sending some data to the cloud computer. This is with the hierarchy, right? So ultimately you are having some, you can say computing node directly connected, you can say, but it is not always directly, but yeah, you can say directly connected to the sensing entity. Then you can say it is the mist computing. It is getting the data from the field and processing there itself, and some process data or maybe some process signal it can forward to the upper layer. It may be edge computing layer or maybe fog computing layer. right? So this is the, I mean, new under concept of the mist computing. So obviously it is not, in that sense, it is not going to be highlighted, because these people's already understand if I need to place a microcontroller near to the sensor. So this is, I mean, just a terminology that people do in their daily life, right? So it is just a terminology to define the mist computing. This is, I mean, just to basically understand the different concept in this computing. Okay. So here you can see this, I mean, one picture that is going to show you the clear cut, I mean, relationship between mist computing, fog computing, and cloud computing, right? So see here, mist computing is obviously at the layer where you have millions of the IoT sensor devices. So it is basically over the sensor network, right? Where sensor networks are going to create, so it is very, you can say, close to the sensor network, right? You put some computing microcontroller, microprocessor devices at the sensor network, and it will be able to receive the data there, and it will process and respond in real time. Okay. And suppose they need basically some higher computing facility, or data need to be analyzed more, then same data or similar data can be forwarded to the upper layer, that's called for computing layer. Or basically we can also have here some edge computing as well. Here you can have some edge computing, right? So that's why in general, edge computing and fog computing are exchangeable. That's why we do not write it explicitly. For computing or edge computing, they are almost at the same layer, but the difference is that in some context you can have the multiple edge computing layers. Then you can put edge computing first, then you can put the fog computing layer on the top of that, right? But in general, we say that fog computing, edge computing is not backend by the fog computing, or neither it is necessarily required to be backend by the cloud computing. Okay, edge computing, we always assume that when there is no need to have upper layer. However, it is optional that you can attach this edge computing devices to the cloud if you want to save the data, or if you want to store the data for future purposes, or want to analyze more. But for computing is necessarily required to be backend by the cloud, right? So this layer is basically, you can assume here can also be actually replaced by the edge computing as well as the fog computing, whichever is the suitable in your context, right? And here you see cloud computing is basically on the top, so you can understand what the density of the device at each layers. It is having millions of the devices. Here for computing or edge computing layer has the thousands of the devices, and it is having hundreds of the devices, right? Because cloud is having very big data centers on the top of that. Okay. So let us understand the difference between cloud versus fog. What are the typical differences? So you can see that these are some parameters. On the behalf of that, you can take a quick read. So if we are talking about the latency, so obviously the cloud is having high latency, fog is having low latency. So delay jitter is basically proportional to the latency. It's, I mean, new way of understanding the delay or basically latency. We have a different formula, but yeah, it is proportional to the latency, right? So it is having high again, it is having very low. And if you talk about the location of the server nodes, so the location of the server nodes is within the internet in the case of cloud computing, and it is at the edge of the local network. If you talk about the fog computing, so it means it will be very close to the, you can say, your data source, right? And distance between the client and server, you can say there can be multiple hops, as Sudhanshu discussed the number of hops we need to send the data from India to US, right? And here we need one hop. It means your whenever you establish a fog server or fog node, then you have to keep in mind that data should be reached to your data center within one hop, right? Or you can say your data center must have the reach so that data can be reached to your particular fog server within one hop. Either you cover one city, either you cover multiple cities. It depends on your basically infrastructure. Okay. If you talk about the security in cloud computing, you cannot define whatever it is provided by the service provider that is there, and because you do not know the location of the server, so you cannot define, right? But here you know the location of the server, so the security can also be defined. Okay. If you talk about the attack on the data and router, here we have the high probability, here we have the less probability. And here you talk about the location awareness. You don't know the location of the cloud computing server, right? But you know the location of server. If you see the geographical distribution, it is centralized and it is distributed. It is, I mean, architectural difference. Okay, this is a very fundamental question. Okay, and if you know the number of server nodes, here we have the few, here we have large, but obviously they are more powerful, right? And it supports the, if you talk about the support for the mobility, here it is limited, and here it is fully supported, right? Similarly, you can see real-time interactions. So these are supported by the both. And similarly, last mile connectivity, it can be wireless line, it can be leased line, right? So in that way, you can understand the how fog computing and cloud computing, right? So we have understood now cloud computing, fog computing, and mist computing, right? So now we need to take a quick view about the edge computing. What is that? So obviously, let us recall this, I mean, picture that we have seen previously. So with edge computing in this one, second option, right? Just it is to recall, right? So let us go ahead. What is this edge computing? So from this picture, you can realize that edge computing stores and processes the data locally, right? On the IoT or mobile device, it was created on. It means the data, it is going to be created where we place some computing device. Okay, so this device is basically this device is able to process the data at the source, right? Or you can say at the edge network, right? So obviously these IoT devices might be creating some network itself, and so you can say this edge computing device will be on their network, right? And only necessary data is being synchronized to a cloud or on a premise server, whatever it is required. It is optional. It is not a necessary component for the edge computing. Even edge computing will also work without having any cloud or any on-premise server. If it is not there, still you will say this is computing is considered as the edge computing. Okay, these are the optional. If you want to do some backend processing, or if you want to do some backup of the data, then you can either you can create a server in your premise, or either you can send the data to the cloud. Okay, so this is you can say this is basically the concept of you can say edge computing. Okay, obviously to connect to the IoT devices or mobile devices, same such you might use the gateways. So because of the gateway, this gateway may connect to the particular device, right? So it will not be that directly you are connecting by a single wire always, right? Might be there will be gateway between the devices. Okay, so just you can read out this, I mean, a few lines about this edge computing. So edge computing is a distributed computing paradigm, right? So again, fog computing is distributed, and edge computing is also distributed computer paradigm, in which processing and computation are performed mainly on classified nodes as smart devices or edge devices, as opposed to processing in the centralized cloud environment or data centers, right? So here, edge computing, again, we have the devices. They are distributed at the different data source location. There, the data is going to be received and being processed at the same time, right? And it helps to provide server resources, data analysis, and artificial intelligence to data collection source and cyber physical source like sensor and actuators. So ultimately, you can say this edge computing can help you out to do some pre-processing. If you want to do perform some more AI-based applications, so it can, for example, suppose you can take the example that way. Suppose I want to see, you can see this is one of the edge computing device. It is in my hand, right? This is called NVIDIA Jetson Nano, right? This device cost is, I mean, approx 12,000. Okay, and this device is basically having computational power more than i3 computer, i3 laptop. Okay, or you can say i3 processor based laptop. This device is more powerful. You can connect any keyboard, you can connect any mouse, you can connect any screen, or obviously this Wi-Fi dongle is connected here, so it can connect. Even you can connect LAN wire as well, right? And this is holding GPU, right? And this GPU is having approx 500 plus GPU cores, and it is having quad core CPU as similar to your i5 laptop. Right, so see, this device is sufficient to do any job, or you can say more than job that you can do on a laptop. So what we can do, this is having GPU, so that's why suppose you want to do develop an application of vehicle count, you can connect this device near to the camera. So there's no need to transfer the live video streaming to the fog server or cloud server. What you can do, you can connect the camera, it is taking the live video stream from the field, right? And yeah, this device is NVIDIA Jetson Nano. NVIDIA Jetson Nano, right? So you can connect this device to the camera, right? And where it is taking the live stream through the interface by which you are connecting. If it is IP camera, it can be connected by the Wi-Fi, or either you can connect by the wired connection, right? So it can take the live video stream and it will be processing at the spot. Okay, and whatever data you want to take, suppose number of vehicles at 1 minute this many, and after 1 minute this many, so on. That same data it can transfer to the cloud by using the Wi-Fi network, right? Or maybe it can transfer to the local server in premise. So this is, typically we called what I say edge computing. Okay, now you can utilize the data that has been sent to the cloud for any reference or for any purpose, or for future any analysis, so on, right? So this is nice picture. This is representing the edge computing scenario. So here obviously we have the IoT devices. They want to so here Internet of Things can be wearable devices, cars, motors, buildings, whatever you can consider, because it is nowadays everything, right? So they are basically performing some data generation operation. So this data might be generated, right? So obviously these devices might be using some sensors or actuators to generate the data. Now this data can be sensed by these devices and it can be finally generated, and data can be collected and aggregated by use some sensor based by using some, you can say some intermediate devices as well, either Arduino or maybe some other intermediate devices, right? Then you can play some IoT, then you can play some edge computing devices, right? So that's called edge IT here, right? And this device can do some computation, or basically it can do some computation, and that based on that computation data, or you can say computer data, or maybe it can also do some analytics because it is having some compute intensive processor. So whatever will be the result after doing this computation by this edge computer devices, that will be stored over this, what I say, data center, or you can say cloud data center. Okay, or maybe on some on-premise server, wherever. But it is not necessary. If you want more processing, you want to do some deep data analysis, then you can store it. Otherwise, it is not necessary. It is optional. Okay. So this is typical edge computing here. So there is some query here. Yeah, difference between mixed and edge computing for both processing elements attached to device. Yeah, it is a really good question. Difference between mixed and edge computing. So see, if you want to know the difference between edge and mixed computing, it is as similar the difference between edge and fog computing, because you cannot replace this edge computing at the mixed level. You can exchange this edge computing with the fog. Okay, and I will show you the difference between edge computing and fog computing later on. Okay, this edge computing is not exchangeable with the mixed computing. This edge computing is exchangeable with the fog computing. Okay, clear? So edge computing, mixed computing is very similar. For example, you want to sense some temperature. Okay, so the temperature sensor cannot do anything because the sensor is no more in use without having any microcontroller. So you can attach the Arduino with the sensor, then you can put into the field. This becomes the mixed computing. Okay.
Sir,
I will come to the one particular slide that will differentiate between fog computing and cloud computing. Okay. Sorry, fog computing and edge computing. So if you see the benefits of this edge computing, it is basically faster. Yeah.
Regarding this,
talk about the 5 key benefits of the edge computing. It is faster response time, right, and reliable operations with the intermittent connectivity. So you can say it is basically near to the edge. So the basically it is having reliable operations. You cannot you can trust that your data is not going to be someone other's hand, or basically it is going to be processed at your device always. And it is secure because it is not going to always to the over public network. You can also do this processing over the local network or basically at the source network. So it will be obviously secure. Then you are sending the data to the cloud or other fog network as well. And cost estimation solutions. Sorry, cost-effective solution. So you see, I have shown you that this powerful device, right? This is how cheaper it is. So it can give you some cost-effective solution, right? Even suppose I will give them an example. I always use this device to make my one system turn on 24 hours on my house because it consumes 5 volts only electricity, right? If I turn on my system, then electricity will be higher. So one device is will be one system will be 24 into on, and I use very big screen to work over these, suppose on overleaf or some Google Doc I want to do, or I want to do some online works. I always use this Unbridge extension. I use its internet connection, and one big screen will be on, so I do not feel that I'm not working on the computer. Okay. So it will give the, I mean, as equivalent speed that I use over the computer, right? So that's why you can see it's cost effective in many ways in terms of purchase as well as in terms of your electricity bill and so on, right? And interoperability is also being supported by the devices, because whenever people start designing such devices, IoT based, then they assume that they will be connected to the different devices as per the they might be interfaced with the different networks or different devices. So they try to keep this, I mean, protocols in mind, that they try to use some open protocols or open standard protocols while designing these devices interfaces, right? So obviously right now we don't have a common interface by which all the devices can connect it, but yes, it is going on the process. Whenever all the vendors will be mutually agreed on some of the protocol, then it will be evolved, right? For example, for the networking purposes, initially we had I mean, lot of, you can say, interfaces. Suppose you are buying device from D-Link, it is not supporting to other device, so on, right? But right now you see that when SDN has been introduced, software-defined networking, now they have, now all the you can say networking communities around the world has been mutually agreed to opt the open flow protocol for the SDN switches, right? The same way that in IoT, obviously it is limitation now in interoperability, but it is expected in future that all the vendors will basically be mutually agreed to basically connect the devices to the common protocol, right? So here you can see that some of the most interesting edge computing devices that you can use. Yeah. So here it is basically Arduino Uno. You guys can use it for the very. It's kind of a microcontroller. It can be used by the most of the sensors. Its cost will be approximately thousands, right? Only, or maybe 1100, 1200 approx. And this is Raspberry Pi. So you can say it is a system on the chip. It is as equivalent to your Linux-based computer system. So it is having its own operating system, Raspberry, or even nowadays it can also support the some of the Linux versions, right? Its cost will be approximately 4 to 5K, right? It will do all the jobs that you can do over the computer as well. And it is NanoPi, you can say, new device. It is the Raspberry Pi, but it is very smaller than the Raspberry Pi, right? You can say it is a size almost credit card. You can keep this device in your wallet, right? And